In this video, I will show you how to use the CAM package built into Fusion 360 to machine this base part of your 3D printer with the CNC milling machine. So first let's open up the base part. If you remember, in Fusion 360 you go to the Data panel, and under your personal projects you can see the folders you've created, and you can find the part that you want to open. And remember, all of these files are in the cloud. I like to close my Data panel so I have a bigger graphic area in my screen. And now we're ready to go to the CAM module within Fusion 360. Right now we're in the Design module. Let's change our workspace to the Manufacturing workspace. Now you can see here that we have all kinds of new tools. Right now we have activated the milling tools. And if you recall, the Maker Lab has 3 tools set up for this 3D printer project. So first of all, let's set up our own custom tool library. That's over here where we can manage tool libraries. You can see here that I've created a custom tool library called ME280 tools, and I've added these 3 tools, tool 11, 12, and 13. You can create a custom tool library by right-clicking on Local and selecting New Tool Library. Once you've created the tool library, you can add tools to it using this new Mill Tool option. Let me go in and show you the different settings for each of these tools. Tool 11, in the General tab, I just gave it a description. It's an 1/8" drill. Under Cutter, I specified some dimensions, the most important of which is that it's a drill tool and that it has a 118-degree drill tip and an 1/8" diameter. I didn't do much with the shaft or the tool holder, but the speed and feed, I put a 3000 RPM spindle speed. The mill in the Maker Lab can handle about 4000 RPM, but I don't like to push it to its maximum. So I put it at 3000 RPM, and then the feed rate is 0.1 of an inch per revolution. That's a decent feed rate for plastic, which means it's about 30 inches per minute. And under Post Processor is where I can label which tool number it is, so that when I post process and create the G-code, it's calling tool 11 for this 1/8" drill bit. Tool 12, under the General, I called it a number 20 drill bit, which is a 0.161" diameter. Here's some specifics for the drill cutter. It's 0.161 diameter, 118-degree drill tip. Again, it's a drilling tool. I didn't do much under shaft or holder, and under speeds and feeds I did a 3000 RPM and a feed of a 0.1 per inch, which correlated to 30 inches per minute. Under Post Processor I specified tool number 12. For tool 13, in the General tab, I called it a 1/4" inch flat end mill, which is 0.250 inches in diameter. In the cutter I specified that it's a flat end mill and it's a 1/4" inch in diameter. Under Feeds and Speeds, again I'm specifying a 3000 RPM spindle speed for cutting as well as for ramping. And then for the feed rates, a 0.005 inch per tooth feed rate, which correlated to 45 inches per minute feed rate for normal cutting. And for plunge cutting, it's a 0.005 of an inch per revolution, which correlated to a 15 inches per minute plunge rate. And in the Post Processor, I specified tool number 13. So that's our tool library. Once we set those tools up, we can now call them within different operations. The next thing I did was I created a new setup. You can see right here I've just accepted the default name setup number 1. You use this tool right here under setup. This is where you can specify. Under setup you can see that I selected a machine, and I just selected this Haas. The setup was a milling type, and then I was able to specify the work coordinate systems, my origin. Under this drop down I decided to specify my origin and my work coordinate system using the XY axis. For the X axis I just chose this edge. For the Y axis I chose this bottom edge over here. And then for the origin I indicated that I want to specify on the model box point, this bottom point right here. And then I had to flip my X axis. You may or may not have to flip any of your axes to get them showing in the correct direction. Under stock I indicated that I wanted the stock to be a relative size box with no additional stock, because we're not going to machine around the perimeter or even face off any of this part. We're going to use just the raw stock and then drill these holes and cut these pockets and slots. So my raw material is 10.5 inches by 10.5 inches by 3/4, which is the exact same overall size as my finished part. Under Post Processor, this is where I can specify a program number. I just accepted the default. And the work coordinate system offset. These are your work offsets. G54 is the most common, and that is what we'll call the offsets that you've set up actually on the milling machine for this origin point right here. Okay, once we have the tool library set up and this setup number 1 created, specifying the stock and our machining coordinate system, we're now ready to create different operations. Here's the tool for creating a drilling operation. You can see that I've created a drilling operation for tool 11 first, those two 1/8" holes, then a drilling operation for tool 12 next, and then a drilling operation for tool 13 for those holes that don't go all the way through the part, and then a drilling operation with tool 13 again for those holes which do go all the way through the part. In drilling operation number 1, you can see the pattern. First of all, you pick the tool in this tab. I selected tool 11. In this tab you select the geometry, and I prefer to select a face of the hole. That way it can find the top and bottom of the hole right from the model. And then in this area I just selected the hole faces, these cylindrical faces here of the hole. Here's where I could specify the heights: a clearance height, a retract height, a feed height, a top height, the bottom of the hole. And here it automatically found where the bottom of the hole was, and I'm going 0 inches from the bottom of the hole. Drill 2, this was with tool 12. You can see for the geometry I again selected the cylindrical faces of the holes. There's 7 of them, 1, 2, 3, 4, 5, 6, 7. And under depths I accepted pretty much the defaults here with exception of the bottom of the hole. It found the bottom of the hole, but I also indicated that I wanted the drill tip to extend through the bottom of the hole, to break through by 50,000ths of an inch. With drill 3, this one's using tool 13. Again, with the geometry I selected the cylindrical faces of those holes. And with the depths I accepted the defaults, including the depth of the bottom of the hole, which was at the hole bottom found from the model. For drill operation number 4, I also selected tool 13. I chose the cylindrical faces of these 3 holes here in the corners. And within the depths, I accepted the defaults here, but at the bottom height for the holes, I indicated the stock bottom because the bottom of the hole in the model actually ends a little higher because it's got a countersink, and we're going to do that countersink by hand again, by the way, so we're not going to worry about the countersink in the CNC milling toolpaths. So I chose the stock bottom for the bottom of the hole, and I also indicated that I want the drill tip to go through by 50,000ths of an inch. The next operation I created was a 2D pocket. That's available here, right here, 2D pocket. And the 2D pocket again follows the same pattern. You choose the tool, tool 13, you choose the geometry, and in the geometry selection you can see that I selected the bottom edge of the pocket so that it knew the boundary. And I selected the bottom edge of all 3 of these pockets. And within the depths, I accepted all these defaults, including the height at the bottom of the pocket, which was just right where I selected the contour. And here under passes, you can see that I have a minimum cutting radius set to 0. And I've selected to pocket this out with climb milling. The next operation was this slot operation. Here's the tool I used right here, a slot. And within this operation, again, I chose the tool to be tool 13. In the geometry selection, I selected the 4 chains indicating the bottom of the slots, this one, and the other 2 on the other side. And for the heights, I accepted the defaults, including the height of the bottom of the slot, which was just at the selected contour. That's why I selected this bottom edge. For passes, you can see what I've specified for passes. The final operation that I created was this 2D contour. It's available right here, 2-dimensional contour. A contour is an operation that allows us to select an edge and have the tool follow that edge. So within this operation you can see I chose tool 13, and then in the geometry section I chose this contour down at the bottom. And under heights you can see that I accepted the defaults here, but for the bottom of the contour I chose to go at negative 50,000ths below the selected contour. That's why I put a negative in there. So the selected contour was that edge there at the bottom, and I want the tool to go through that, not just go up to it. And you can see what I've specified for passes. Basically it's going to do it all in one pass. And because it's plastic, we could do that. If it was metal, we'd have to specify several different passes to get down to that depth. But in plastic, we can do it all in one depth. Once we have these operations defined and the tool paths created, we can simulate them to make sure they look right. If I just right-click on my setup, I can specify to simulate those tool paths. In this little window right here, I can specify how I want to see the tool paths. I like to turn on stock and to turn off the tool path. And then here's the player right down here at the bottom. You can speed it up, slow it down with this bar, and hit play to see the tool paths. It drills the holes. So now that I have simulated that and like what I see, I can now post-process those toolpaths to create the G-code. Here's the tool for post-processing. Choose Post-Process. We can specify where to save the file. It's just a text file. Even though it has a .nc extension, we could still just open it in Notepad or any other word processor because it's just a text file. Here's where we pick the post-processor that we want to use. And I'll just choose this post-processor right here, the Haas Pre-NGC. And let's post-process. Let's search for the folder where it will save this text file, and we'll choose Save. Here's the G-code it's created. You can see it really is just a text file. It's automatically opened it in this Visual Studio. I could have just opened it in Notepad or Microsoft Word just as easily. This is the G-code that I could save onto a flash drive and take to the CNC mill in the Maker Lab.